see.
Of course they have. Without thinking about it.
Yeah. Well, I think Jess has left.
Robertson.
Yeah. It was big. We have a new senior BA.
So, welcome everybody. Tonight I'm going to run back. I redid a few slides to give a bit more information on some stuff. So going back to the along wind response, before we go back to the crosswind response that we were talking about last week, or where we ended up. This was the equation that gives you the dynamic response factor between the peak static load and the dynamic response. And this is just a breakdown of all the components that go into that. So you've got your background factor, which you can see is a function of the height of the structure. S is the level of the building that you're actually measuring the response at, the width of the building at the top, and the turbulence length scale, LH. And essentially what that is giving you is the integral underneath the force spectrum from the background component, okay? So that's what that bit's telling you. And your turbulence length scale is just a standard value based on the height above ground level. HS isn't important. It really is the height that you're measuring. It's a factor up the building where you're measuring the response, okay? So if it's down at ground level, S is equal to 0. And if it's, you may have a level where your building changes structure. The structure may get simplified and you may want to take the measurements at that point. And that's where your S will change. And if you do that, then the factor will actually increase your C down. C down will go up if you make the area of the building that's important to the resonant response smaller by lifting that resonance, then that bit of the building can be more enveloped in a gust, and therefore you get a bigger response over that component. Make sense? Your size reduction factor is again based on natural frequency in the long wind direction, the height of the building, and the width of the building. So it's basically a big geometry thing, and the speed of the mean wind speed of the flow, which is that component. And that is to do with the aerodynamic admittance function. So it's a size reduction factor based on the size of the structure. And then you've got your turbulent energy factor, which is a function of the reduced frequency. And the reduced frequency is normalized, the along wind natural frequency, the turbulence length scale, and the mean wind speed again. And from the pictures that we had previously, you've got your along wind natural frequency. It's giving you the energy in the along wind at that natural frequency. And so if we go back to the previous slide, you take the background component and the resonant component, and the resonant component is essentially HS times S times ET over zeta. So you're taking, this is your response now, and since that's your force, and at that point the mechanical admittance function is essentially 1 over that entire area, then that's why you get this. This is the BS value, and that's your resonant component. So if we're talking in spectral senses, those are the variances of the response. And that's why when you come back to here, if you think of these two components, the BS and the SET over zeta is your variance of the response. You're then multiplying it by the square of the peak factor, and then taking the square root of it. So, and this is essentially the square root of the sum of the squares. So you're never going to have the peak background response and the peak resonant response happening at the same time. And that's why you combine those two peaks as in the square root of the sum of the squares to give you an indication of what the proper peak would be. Happy? One happy? It's just digging more into the equation to try and give you more information on how to dig into the code and delve and amend it later. Now there was another one that I did here that I realized when I talked about the peak response of a chimney, a lightweight chimney last week. Put this slide up. I realized that was actually the 2011 version of the standard, not the 2021 version of the standard, and it's changed. So I've included this because this is important for assignment 2 because you're going to be using this section in the equation. So instead of what you had previously, you've now got that the maximum displacement is equal to peak factor times a maximum crosswind standard deviation. And the ratio of that is given by these functions C1 and C2, which are here. And these constants A, L, K, A, and CC are defined in this table down here, depending on your various Reynolds number for the chimney. Okay. The problem with the current standard is they've got that equation for your Reynolds number in it, which is wrong. Okay, and you should be using that equation. Okay, so you're getting ahead of the game because this is going to be a change that comes out in correction 2 of the standard. The reason it is that this is based on B des theta, which is your design wind speed. But this response is at your critical wind speed where you've got the vortex shedding frequency matching your natural frequency, and it's not necessarily the ultimate limit wind speed, which is what that was. Yeah? And so that's what the equation should be to correct for it, where ST is your Stroh number, and that's defined in the standard as 0.2 for a circular element. Okay? So this slide's important for assignment 2. It's up on Canvas, so you don't have to take photos of it. This is essentially because structural engineers don't like viscosity. This is your Reynolds number. We just put it as a constant. Simplifies life for people. So that's important. The load per unit height hasn't changed. That's not really mass per unit height. That should be peak load distribution up the height of the chimney. It's based on that. It's not mass per unit height. I'll change that tomorrow. Okay. So that's the change from that one. It's still based on Scruton number, but this technique was found to be non-conservative for certain Reynolds number ranges, so which is why these ones have been brought in. So it's Reynolds number dependent. Okay. Then we talked about interference, and I think that was this last slide last week. Is that correct? Oh, right? Okay. So we're looking at buildings now. So we're moving away from the lightweight structures. We're moving into building responses, broadband building response. We're not looking at, this is a combination of all the different mechanisms that you can have in the crosswind. So you've got your turbulence buffeting, you've got your wake excitation and you've got your motion dependency. Everything sort of gets clumped into one because it's difficult to separate them all out. So when you start looking at your cross-force wind spectrum, it's based on this standard deviation of crosswind force spectrum coefficient, this little coefficient that's just been thrown in there. And that is an absolute difficulty to calculate. And the easiest way to do it is through wind tunnel testing. That's where it's all come from in the past, and all the information is in the standard. And a lot of this lecture tonight is going to be talking about that coefficient. Okay. So this is giving you the first mode response. So we're assuming the building is just again working in one mode. It's first mode. It comes into this equation. So that's your standard deviation of y, which is the displacement in the crosswind direction. 1 over 2 pi nc, where c is the crosswind natural frequency rather than the alongwind natural frequency. The mass of the structure, or the modal mass. And then the natural frequency, that should be an nc again. The lift coefficient in at the crosswind natural frequency, and then again dividing by 4 zeta AS, which is your structural damping for the system. If you normalize it, this function, then you can have your CFS comes down to this. So we've got the spectrum, the frequency times the energy in the crosswind direction, and we're just normalizing that. So that's our lift spectrum, so that's Newton squared per hertz multiplied by hertz, so that's Newton squared, and then you're essentially dividing it by Newton squared, so you're half rho v squared. Again, note that this is the mean wind speed at the top of the building, not the gust wind speed, so which is why when you go to the standard, you've got that 1 plus g sigma u component in there. So that's mean, because it's much easier to do that in the wind tunnel to measure mean wind speeds. And then you've got B times H. So the width of the building, height of the building. That's your logical one. Although you could argue that B is not logical when you're talking about crosswind. Because when the wind is coming onto the building, B is the crosswind, is the width of the building, which would be in the along wind direction. You could argue that it should be that dimension, but it's not. Okay. So again, experimentalists, they've gone and done it, and they've normalized it how they want to normalize it. Yeah. You go back, you could do additional testing, and you may find that what they've done is incorrect. Right. Now the challenging slide. And this will be slightly different from the ones in your notes because I've put in a few things this morning. If you're looking at your loading spectra, or your force spectra, in the along wind direction, you'll have the red line, and in the crosswind direction, you'll have that pink line. So if we interrogate that more, you're saying down at your low frequencies down here, where you've got the turbulence coming in, you're just saying that you've got more energy in that direction than you do with the lateral turbulence, which is putting the crosswind force into the building, okay? So that's a way that you can easily tell, if you're given a graph of along wind, crosswind, and torsional loading, yeah, that's the first thing to look at, along wind, crosswind. What's got more energy? Okay. Maybe slightly different if you've got a really skinny building, but you'd have to think about that in your response. Okay. But in the crosswind direction, you've got this hump. That hump is coming from the vortex shedding process. So that the fact that the vortices are coming off your body is inducing a frequency. Now, it's not a spike. It's not all going to, because the wind's not coming at a constant speed. So you're not going to have a constant frequency of vortices. So you've got this broader band hump, okay? That's another signal of what's a crosswind spectrum in your books. Okay? So this the main graph here is a graph of this normalized spectrum. So this is CFS that's actually in the standard. And the CFS in the standard only deals for buildings of 3 to 1 to 1 aspect ratio. So 3 height, 1 width, 1 depth. So a square prism. 6 to 1 to 1 and 6 to 2 to 1. So 2 to 1 in plan and 6 times that in height. So if you've got any other type building, you can't design for it in the standard. Okay? Just can't do it. Any other shape, you've got to interpret it. So this is giving you a little bit more information to design other buildings of different aspect ratios. And we'll get into the nuts and bolts of this in a minute. But this is plotted against wind speed, so reduced velocity. So wind speed is increasing in this direction. Okay? Or it can be plotted as reduced frequency, just to confuse people. And it works. Yeah? But that's essentially your Stroh number. But reduced velocity, you can think of this as increasing wind speed in this direction from right to left. Okay? Now this is not, think of these as the actual response, so the integral underneath the spectrum of the response. It's not, this is not a spectrum. This is the result of integrating the spectrum at lots of different wind speeds. So if we take that, take your force spectrum, for instance, and you increase the wind speed. Yeah? Just normally increase the wind speed. You're going to generate more energy. There's more energy in the flow at fastest flow. Okay? Now, if this was ideal and you normalized everything, those two results would collapse onto one another and you would get a single result. Yeah? That's what this is being drawn to do. Now, in real life, though, and this is where you start to get to question wind tunnel testing techniques that we'll get to in a couple of weeks, is this is assuming that your vortex shedding process is also going to scale up. In other words, your Stroh number stays the same. At all your different Reynolds numbers, your Stroh number stays the same. Now that is a big query, yeah? But that has huge implications for base balance testing, because we'll get to that in a few weeks. But what would happen if Stroh number did change is that this hump would slide up and down the curve. Okay, because you've got two processes going on here. You've got the turbulence buffeting, which is generating the general curve of that, and then you've got the hump, which is a vortex shedding process. Okay, so the assumption here is that the Stroh number is Reynolds number independent. If you're doing base balance testing. If you were doing air elastic testing and you modeled the actual structural properties of the building itself, then it'll bring it all into the testing technique. Okay, so this is your first plot. So this is your lift spectrum, and it's just showing you that if you increase the wind speed, that's what's going to happen to the the flow to the energy in the system. Now, in the previous slide, it mentioned B star is the effective bandwidth of the spectrum. So that's why there's something in the next slide on effective bandwidth. So your dynamic amplification function, the one in the middle here, that's fixed on the structure. It's not changing. Okay, that's fixed. In your displacement, this is your response. Your displacement response is equal to that spectrum times that spectrum. And you can see that wherever your hump is, if you hump here, you're going to get a large spike. And if it moves up here, then you're also going to increase the magnitude of it. But above that level, you don't pick up this hump anymore, because this hump's getting multiplied by this bit in the dynamic amplification function, which is an exceptionally low magnitude. So you get no response out of it. Yeah? So you don't see this hump. If we actually move this one back a bit, then you would start to see a small hump generate over here. Okay? And then if you integrate under that, the response spectrum for each wind speed, and then you normalize it, that is what is plotted on this curve. So each wind speed, we can integrate underneath the spectrum, giving you this component here, and then we're going to normalize it by this. So if we were to plot that bottom graph and normalize it by u squared, these humps would collapse onto one another. And all that would be left would be the spike, which would be changing in size, because you're coming to a different point here. Okay? And that is your effective bandwidth, that bit of interest that's around the resonant component. So that's what this plot is doing. It's doing a test at lots of different wind speeds. It's measuring your lift response, normalizing it, plotting it. Here. Now, if we didn't have any wake excitation, you would get something that looked like that. If it was just turbulence buffering, okay, and we've got no response coming from wake excitation, it would be like that. It's going to be related to velocity squared. Yeah?
Can you just explain turbulence buffeting again?
Turbulence buffeting. Yep, definitely. Got a building or an object. You've got the wind blowing on it, and it's got turbulence in it. And that is really the dynamic load that you're getting onto the building. Okay, so if you've got big gusts that are coming through, yeah, they'll envelop the whole building and it'll move over. If you've got a little gust that comes over, it's probably not going to do too much to the overall building response. And because the turbulence is acting in 3 dimensions, you are getting a lateral load onto the building as well, because we're looking at the crosswind response now. So if the wind's coming this way, we're looking at the building going in that direction. Yeah? So that's what this is looking at, okay? So that's your turbulence buffeting. Just the punching of the wind hitting the structure. And not the vortex shedding process, which is your wake excitation. And I'll labour all these points because really that's what this course is about. Yeah? Your different excitation mechanisms. Okay? So hopefully that shows you, because you can see here where these curves are coming down. They're coming down to this sort of line. They're sort of coming down here. And then at the other end, when you get to a higher wind speed, they're turning around over here. So that is your wake excitation mechanism. If you can understand this plot, it goes a long way. And I think what I've added in here is hopefully going to make it easier for you to grasp what's happening. So if we now look at the actual graph itself, what's on there, if we've got a square building here, so it's gone from 3 to 1 to 1 high, 6 to 1 high, to 18 to 1 high. So it's just getting taller. Okay, keep the plan dimension the same, it's just getting bigger. So if you look at each of those, you'll see the 3 to 1 rises up to here, 6 to 1 here, 9 to 1 and 18 to 1. They're getting higher. But they're also getting skinnier. Okay? Classic final exam question. Why? Explain that graph to me. Why does it do it? Why does a 3 to 1 building give you a smaller response at that reduced velocity compared to an 18 to 1 building? Jordan?
It's because it's not seeing as much wind as the taller building, potentially.
Not seeing as much wind.
Not as much force causing and not as much area for the vortex shedding to
On the 3 to 1 building. Yeah? I almost give you a mark for that. If we look at, on the right track, if we look at a 3 to 1 building compared to an 18 to 1 building, and you imagine the flow that's going around those structures. 3 to 1, you've got a lot of eddy that's gone over the top, 3-dimensional flow. So your vortex shedding process is only getting really applied to that chunk of the building. If you look at the tall building, you've got the same flow coming over the top. So, but now you've got this amount of building that's giving you the vortex shedding. So it's much better correlated on the tall building than it is on the short building. And therefore you get a bigger response. And in this case, you've got your reduced velocity is about 10, where you're getting that peak, which corresponds to a Stroh number of about 0.1, which is what you would expect for a rectangular structure. That's where you're getting the peak resonant response caused by the vortex shedding aligning with the natural frequency of the building. That's where you get a big response. Easy. Lauren, next one's for you. Why, over here, have we got the 3 to 1 bigger than the 6 to 1 bigger than the 9 to 1 bigger than the 18 to 1 It's flipped around.
Something to do with higher frequency of vortex shedding.
It also does it to a lesser extent over here. Your 18 to 1 down here, and these are all messed up. Yeah? I'm specifically talking about this end of the spectrum.
No idea.
No idea. Honestly, I like it. Anybody like to comment? Anybody like to hazard a guess as to why it's flipped around? reduced velocity are we working at? Slow. Would we be expecting the frequency of the vortex shedding to be aligned with the natural frequency of the building? No. Yeah? Because that happens at 10. So when we move further and further away from here, we're separating the natural, the vortex shedding frequency to the natural frequency. So we're changing the excitation mechanism. We're changing it from wake excitation to turbulence buffeting. Now, does that help you answer the question? We've now got the fact that we're dealing with turbulence buffeting. Why does that affect a smaller building compared to a big building? Back to you, Lauren.
Is the question like why is turbulence impacting
3-to-1 building much more than an 18-to-1 building? Want me to keep going with the hint?
Is that suggesting that the wind frequency has a higher energy at the lower height than it does at a higher height?
It's hopefully suggesting that a building this size is being affected by all that in the spectrum. Yeah? Because all these little gusts are also impacting, enveloping the whole structure. Whereas the 18-to-1 is only being affected by that amount of energy in the system. Because you've got to have a gust that's that big to really envelop it and to cause any loading issues. Okay? So this one is much more sensitive to turbulence buffeting in the wind.
How distributions of velocity show higher velocities as you go. How doesn't that correlate to higher frequencies when you go up?
Higher frequencies of what?
Of wind.
This is telling you the mean wind speed, let's say. And if we go back to, it's really that graph at the top. So as you go higher and it gets faster, you will have more energy in the wind at bigger frequencies. So this is just essentially getting exploded out the way. Yeah? It's not as extreme as that when you're looking at this. More extreme when you start to increase that faster and faster. So yes, you're only looking at down here, you'll be looking at something like you've got a load spectrum, something like that, and then up at the top, you're probably looking at something that's just a bit bigger, because the speed's not different. You've also got less turbulence up here. Yeah. Which will also affect that shape. These are all good final exam questions. Okay? So there's your turbulence intensity. down here, you've got a lot more turbulence in the flow, which is also going to be impacting that more. Yeah.
So you're saying it has to envelop the whole structure to cause?
It doesn't have to. It
Oh.
doesn't have to. It's just.
It's more impacted.
It's more
the
impact.
whole thing.
Yeah, because there's more eddies in the flow that are going to be impacting the loading on the small building than the big building.
A lot easier to envelop the whole small rather than.
Correct. Yeah. Yeah. Any other questions? Probably speak for 2 hours on this slide. What about the other end? Over here. Look,
What about it?
what about it? Why does it get all messed up and it's not in a nice orderly manner as we would like in engineering?
So, if you look at the other end, that says the wind's getting faster. And they look like they're kind of coming together.
They're coming together, yes.
Yeah.
Yeah. So, what does that tell you from a non-dimensionalized manner?
I guess, well, that the response is not, like, on the other side, the response starts to become turbulence buffeting rather than wake excitation. Same case for the other side, it stops being too fast for patient.
Yes. So the eddies are going like this, and the building's trying to go like this. Yeah? So if you think of your mechanical admittance function, your loading's the way over here. Your vortex shedding frequency is now way, way, way over here, that hump. And so you're getting none of it. That's why they all collapse. So as you get faster and faster and faster, yeah, you're really, in a non-dimensional sense, if you non-dimensionalize these, you would collapse. And if you make it faster, you essentially just move this way. Okay? And then, regardless of what's happening, you've got the same spectrum, the same hump, and therefore you get the same response. If you go the other way and you slow it down, you're moving everything this way. And it's this tail of the spectrum that's going to be changing. That's why it gets messy down in here. You've also got less of that effect as well at faster wind speeds. The only other note on this one, well, the other note is, that's your typical building operating speed for your normal building up to 100, 120 meters sort of stuff. Once you start getting taller than that, then essentially your mechanical admittance function, you can think of it as moving this way relative to that spectrum, okay? And you can get cases where you've got really tall, skinny buildings where at ultimate limit state, you're actually operating at this reduced velocities greater than 10. Okay? And then when you actually reduce the wind speed and get down to, say, serviceability limits durations, you actually increase your dynamic response, which has huge issues for serviceability in tall buildings in terms of accelerations, because people get sick. The building's moving much more at a lower wind speed, and people feel sick inside the building. The other one I was going to mention was this dotted line over here, which is circular in plan rather than square in plan. And you can see that that shifted over to here. And you've now got a critical reduced velocity of about 6. Does that make sense? Yes, hopefully, because that relates to a Stroh number of about 0.2, 0.22. Yeah. And as you saw from the previous slide when we were looking at chimneys moving, the Stroh number in the standards is fixed at 0.2. So we would be expecting the peak response to be happening in this zone. And it is. Physics works. Anybody got any questions? Yes, Tom.
Yeah, so why is it then that the response is larger in the low frequency case?
For
Just overall, you can kind of see that yeah, on that end it's quite a bit lower than on the left end. Yeah.
because it's
Because
buffeting
the buffeting is, yeah.
thing, and the turbulence buffeting is going to increase with v squared.
Yeah, sure.
Yeah. So faster you go, the more turbulence you've got hitting your building, and therefore you bigger your response.
The more meaningful the turbulence is.
Yeah. So that's why that blue line is doing that as a sort of sketch indicator. Because again, if you think about what's happening in terms of your spectrum, if we normalize that spectrum, so it was just like this, yeah, and there's our mechanical admittance function, all we would be doing is, if it goes faster, this just migrates this way. Yeah? So you're now creeping up the slope until you get really, really, really quick. But that's well beyond design wins.
Design a building on Neptune.
Go, Lauren.
Why does that response function move leftwards if it's tall, if the building is more tall?
Why does the
Yellow curve. I think you said it moves left, like the peak moves left.
this one,
Yeah.
if the building is taller,
Yeah.
then the natural frequency of the building down. No. Got a ruler? No, you don't have a ruler. Has anybody got a ruler? We need props in this lecture. If you take a ruler and you twang it off the desk, yeah, and you have it really short, do you get a high frequency or a low frequency? 50-50 chance?
Right, yeah.
And you blew it. Yeah, it'll be high. If you make it long, it goes boing, boing, boing. Yeah, you get a low frequency. Same with the building. It's just a cantilever. So the taller you make it, the lower the natural frequency. So if this is getting lower, this is going to move this way. Yeah. Thing is that all these things can move relative. That's why it's difficult to do this lecture, because things can move depending if you normalize them, don't normalize them, and so on. Yeah. Sort of important to sit down and mull over this one over a glass of wine or something like that. Yeah, let's just think about that. It'll make more sense. If it starts to blur and we're about, you've drunk too much. Any other questions? This is a good one. This is a good slide.
I have a question. That seems really restrictive, like 3 to 1 to 1, 6 to 1 to 1. So if you have a non-square cross-section, can you do anything other than wind tunnel testing?
Throw your down in disgust.
Okay.
Go and do research. Read the literature, because some stuff has been done on different shapes of building. But again, this is for a 13 to 1 height ratio. So it's, you know, pretty big stuff, tall, slender stuff. Again, all this stuff is done in isolated buildings as well. Let's not even just think about the aspect ratio. When interference is probably the key thing that would drive you to do wind tunnel testing or more advanced studies. Different shapes, there is published information out there on them. They may not be in the right format to take it and just dump it straight into CFS values to put into the code, but you've now got the tools to say, right, well, to get it into CFS format, I need that. If they've done it and if the research has done it and they've normalized it by a different thing, you can renormalize it and collapse it back into CFS format. Put it straight into the standard. So really the purpose of these lectures is to sort of give you the toolkit to go away and use published data and to expand standard so that it's not just a 3:1:1, 6:1:1 building. And when you do assignment 2, you'll get to use the output depending on the shape of your block. We'll talk about the assignment later because it's all based on your house. You're going to put a high-rise building on your house, yeah, and design for that. If you've got a long, skinny block, you're going to have a long, skinny building, and therefore it's not going to be code compliant. Very few people doing this course actually get a code compliant building. So there's the challenge. What do I do? Too hard. I'm not building it. Developer will tell you off. You won't get paid. Yeah? So engineering judgment, and that's what this is about, to give you confidence in using the code and stretching it and saying, well, if I do this, I could be conservative, or if I do that, I could be conservative. Yeah? Or I can be non-conservative. Let's really nail this down depending on where you stand philosophically as an engineer. Are we in the, I want to be exceptionally conservative so nobody's ever going to sue me, or I want to minimize use of materials and save the planet? Can argue it both ways. So teach you the tricks that you can use to try and hone in on what you're looking at. But again, you're coming back to when you start looking at say a 6 to 2 to 1 building. So in plan form, you're looking at something, that is that, but it's looking something like that or like this. Would you imagine that these would deviate significantly from the 6 to 1 to 1 curve on there? Yes, sir. Got your hand up, Thomas. You want to answer?
Well, there's going to be some little bit of if the flow reattaches or not, but
Some little bit about flow reattachment. Absolutely. So this one, with the long after body, the flow is going to reattach. And you're going to get this narrow wake. So if you were plotting same graph, sorry, that's about it, and we've got reduced velocity going in that direction over NB, we would expect it to do something like that. It's not got a hump anymore because you're not going to get the vortex shedding to happen. Whereas the top one, it is going to fully envelop down here, and you're probably going to get a fiercer interaction between the shear layers, and so you more than likely get a sharper spike and probably taller than the 6 to 1 to 1, which may be broader like that. So again, coming back to the flow visualization and what we've been talking about for the last 4 or 5 weeks, you can sort of lead it into your discussion. Yeah? Question is, where does that point come that's your crux. Yeah, and it's about an aspect ratio of 1 to 1.3-ish. 0.62 is an after body length. Yeah? So, you know it doesn't do it at 1, it's got to be longer than 1, because that's still got the hump. The longer you make it, the better it becomes, and the less, the flatter this hump will generate beats. So it's a case of trying to absorb all this information and then distill it into your, and I know it's difficult and there's a shed load of information there, but to get the fundamentals into place. And you said there, Toma, long after body, flow's going to reattach. Flow reattaches, you've got a narrow wake. You can feed that back into your thought process. Everything comes from flow visualization. Everything. You can visualize it, you make your life a whole lot easier. So there are published stuff. This is more work by Barry Vickery that we've talked about quite a bit in this course. It's come up quite a lot, but here's mean coefficients for various shaped structures fluctuating around there. And from a series of dynamic tests, air elastic tests, I've probably got to go back. All this stuff was done on air elastic testing. Okay, so not base balance. It was all done on air elastic testing. And an air elastic test in the wind tunnel is you model the natural frequencies. The building actually moves in the wind tunnel. Most wind tunnel testing is done on rigid models. Okay. Costs more to make a model move. That's why it's generally done in academia, because people have time to sit and think about things. So an air elastic test, it moves in the wind. And the building, as it moves in the wind, if you think about damping, the more it moves, the more it's got to push back against the wind, and therefore you get aerodynamic damping out of the system. We did talk about aerodynamic damping last week or the week before. Okay, just as the object moves. So that's what was done here. So you put the model in the wind tunnel. These ones were done on stick models. So essentially you've got a rectangular bar that you put strain gauges on, and then you put a carcass of the building over the top, and you put it in the wind tunnel, and it moves from side to side. Okay, change the wind speed, see what the response is. Change the wind speed, see what the response is. So you do all the tests at different wind speeds, and you can also do the tests at different damping levels, different frequencies of the building, and so on. And then all the data has been collapsed down into these curves for different aspect ratio buildings. So it does take a long time to do the tests, which is why there's such limited data on it. And it's pretty technical stuff. Boring. A little bit boring. You know, change the wind speed, see what happens. Change the wind speed, see what happens. Can be boring. So these guys did a whole series of shapes. And out of that, they've got lots of coefficients. So regardless of the shape of the building, they've collapsed it down so that your mean moment coefficient is your moment divided by that, or your peak is equal to your mean component plus peak factor times your standard deviation times another function. Okay? And then all these constants you measure from all your testing that you've done. So you've got basically a shopping list like this. So you've got mx would be a long wind. C bar is your mean coefficient, your fluctuating coefficient, and all your C1 plus C1 to C5s, which are all down in this equation for your spectrum, if you want to plot the spectrum out. And then you've got the my as well. So you can start looking at your long wind and crosswind responses. Here you've got the Stroh number for a hexagon is 0.135. Makes sense. Between 0.1, 0.15, that's what you'll be expecting it to be. And there it is, as if by magic. Works, okay? So once you've got all these, as long as you've got a 13 to 1 to 1 building, or a 13 to 1 building, then you can do some estimates of what your wind loading is, okay? And that's what they look like if you plot them out in terms of energy in the crosswind and along wind direction. This is your long wind, or I should say X direction and Y direction, because the triangular ones don't actually go in line. So the triangular ones, we've defined the axes as X and Y. Why they didn't just spin it round so that the wind was on L1 and had X and Y. Let's not go there, okay? The art of presenting data. So this a long wind one at the top, it's got the two ones with the hump in it here. But that's essentially a component of the crosswind response. You can see here, so this is essentially a reduced Stroh number, so reduced frequency. So wind speed has gone in that direction. And you can see that this is a spectrum, sorry, that you're getting the curve as expected with a hump in it. And then if you look at the crosswind response, they've all got humps in them. It's just the relative size of the hump. So the sharp face, like the 3 to 1 rectangle, wind's gone that way, you would expect that to have a fairly sharp spike, and it is. It's that green one. And then your 1 to 3's got the soft spike, where you've got the long afterbody. You don't have that significant spike in the system. So this is sort of data that's there. And then if you've got your height, the width of the building, then you can predict what the spectrum's going to be. Once you've got the spectrum, you can start doing all your calculations with it to work out what your response is going to be. That was an exam question one year. Interrogate data like that. So it was soft. It was a soft question. Back to the standard. We're looking at the dynamic response again. And so the key bit that we've been looking at is the CFS value. That's coming from a graph that's looking at this. It's now plotted the other way, just to confuse you. So wind speed's now increasing left to right. So again, if we took what would be happening if it was just turbulence buffeting, it would be going from low up to high. But that's your vortex shedding piece. This will be for a 6 to 1 to 1 building by the looks of it. So you calculate what your reduced velocity is, and that gives you the log 10 of your CFS value, which you can then dump into that equation. It's all this different plot to the previous plot, so it's on a log scale, a log 10 rather than linear scale. Okay? So that's the only component really in the equation. All this other stuff is to do with the building properties. So your mode shape, the peak factor in your wind speed. That's your aspect ratio of the building, so calculate the force, and then you've got your peak factor. So the only thing that's really aerodynamic about this is that CFS value, and that's purely empirical from wind tunnel test results. Okay. And that's why this is complicated to extend it to other things. I mean, you could do it to other building shapes and forms, but then your standard goes from being that thick to being that thick, and nobody uses it. So it's pointless. You better go into the experts in the field and say, tell me what's going to go on. Whether you look up research to do the analysis, which is what you guys can now do with confidence, or you go and do wind tunnel testing. So again, crosswind response, you're only looking at this thing vibrating in the crosswind direction. It's not a sinusoid, it's not flipping back and forward, it's going over, and then it might get a bit where it's going higher and then it's going down to lower. You know, we're looking at the broadband results or the narrow band results in terms of response. Most of this stuff is going to be broadband. You're going to have amplitude of response is going to increase and decrease, and it's always going to be changing. It's not going to be locked in as a sinusoid. So this is your standard deviation component. You're going to multiply it by your peak factor to give you your gust response, your peak response in the system. So that's how it's incorporated into AS 1170.2. Questions? And yes, you will be using this in your assignment too. So that's nice and easy, relatively speaking. Isolated building in the middle of nowhere, no surrounding buildings. What happens if you put a building in next to it? New structure. We've dealt with this before. You're changing the loading spectrum because of the way that the flows come and do. Even if you were doing this in terms of just your classic streamline effect, you'd have your streamline coming through here. It's got to work its way through here, and you would be expecting faster flow through here, just from a mean sense. Add your dynamics on top of it, and it's complicated much more, because you've got the fact that the shear layers from here are interacting with each other, the shear layers from here are interacting with each other, but the shear layers from all four of them are interacting with each other, which is again ending your dynamic loading on the system. Change the spacing, change the shape, change anything, and you'll change the interaction and the response. Can you codify it? Not a chance in hell. There's no way that that could be codified. Again, publish data. Find out what's of concern for you, for your building, working on here. So again, interference effects. There's your response. If top one, target plot. So if you turn the wind off, then end up with a dot in the middle. Turn the wind on, moves over, will vibrate in the along wind direction, it will vibrate in the crosswind direction. Sort of ellipse of response that you would get. This is at a reduced velocity of 6. Invert it, give you your Stroh number, about 0.14. We just solved it for a hexagon, it was about 0.135. So this is about your critical wind. Okay. Put another building in, downwind of it, then your upstream building does that. That's a huge change in your response.
Yeah.
Massive change in your response. And it's all because you've affected the flow patterns and the dynamic interaction between the shear layers. It's ripe for research. If anybody's got no time and want to do a PhD, here's a topic. Here's some stuff that's been done in the past. In fact, here by Suki. So here's buffeting factors. Essentially, you're taking the response for an interfered with building compared with an isolated building, and you're given the ratios. So there's your measured building. And these plots are for what happens if you put another building anywhere in this matrix. Wind's going from left to right, should do. If you've got a building here, that tells you standard deviation of your crosswind response, standard deviation of your crosswind response. Standard deviation of your crosswind response. It's this bit. Goes up by a factor of 80%. A massive increase in the load. Why? Again, classic exam question. Explain this graph to me. One-liner, simple question. The responses that are important. How deep do you go into this? If you got a building here, well, what is the flow pattern? What's generating this exceedance? Your vortex is coming off here, and it's hitting the side of this building. This line here, you can see there's a sort of zone that's coming in there. It's probably about 15 degrees round. 4, so 8 to 2, yeah. It's about 15 degrees, okay, which is your expansion of flow. The flow is coming around here, and it's hitting that side. But because it's a vortex and it's coming in at a frequency, you're getting that interaction. It's giving you that much bigger load. So you're changing the excitation frequency in the crosswind direction essentially from that. This is what would be happening. But on the downwind side, in fact the upwind side it's probably doing something like that. But your downwind side it's doing something like that. Because you've got all the frequencies within the shed vortex. It's combining into. When you get too close, though, you can see that it starts to drop. So even you're 2 widths upstream and 2 to the side, or one and a bit to the side, you get a reduction in your loading. Why? Anybody like to suggest a reason as to when you've got your structure close in, you get a reduction? Come on.
Shielding. The wind's not hitting it as much.
Not hitting as much. I'll give you half a point for that. We go back to the videos. These are all deliberately more than sort of 1, 2 widths apart of this small thing. Because if you start to move this closer, these 2 vortices are trapped. They can't fluctuate as much. And so you've only got the outer sides that really have a shear layer, let's say. You may have a jet coming through the middle, but it's not going to be fluctuating. Wow. So lights are back on. So that's the reason why when it gets so close together, you've squeezed the flow through there. Yes, you've still got flow, but it's not going to be changing the separation point. And therefore, you're not going to have that interaction. Hence, the response goes down because you've only got the vortex being shed on one side, really, that's got a dominant fluctuation, rather than on both sides of the structure, and therefore you get a lower dynamic response. So these are for a long wind and crosswind response. So a long wind response, you come in a little bit. It's like there you come in, but you've still got this line through here, which is slightly inboard from here, because you now want that vortex to hit on the windward wall and cause the fluctuation, rather than in this case where it's hitting on the sidewall. So this is your long wind response, the crosswind response. In the long wind direction, your critical aspect is when you're actually downwind. That causes back pressure to form, affect the leeward side of the upwind building is getting affected. That's why this is so dominant in that case. Pretty much everywhere in the long wind direction, interference is a problem. Everything's greater than 1 in that case. So that was, these ones were for an identical square building, and these ones are for a circular building. A circular building on a square building. And in crosswind, you can also see that your crosswind response gets increased when you get it directly upstream as well. And that's because your vortices are impacting, they're coming back in again and impacting the side of the building again. And that's what you're seeing in this case for your crosswind response, for your long wind response where it's shedding directly onto it. Changes shape a little bit, but so hopefully you can see that interference is can be a big issue. So if you're designing buildings, again, there's only 2 buildings here. So you've got to have buildings that are spaced apart. Somewhere like the Gold Coast, if you know the Gold Coast, you've got maybe 1 building every block, every 2 blocks. High rise. This is when interference, the alarm bell should be ringing. You should go, this is not going to be code compliant. It's probably going to have an interference effect. The code does not consider interference on anything. So you guys are ahead of the game. Here's another one, smaller interfering building to a slightly bigger building. Again, they're all orthogonal, they're still prismatic. You would expect prismatic buildings to cause greater interference than a tapered building or a step building or an oddly shaped building, but you've always got this, and it's that a long wind buffering is normally the key problem, because it induces that impulse load that causes acceleration issues in the building. And occupant comfort, this spacing is normally. So, just a few examples. In this case, it looked at a long wind, crosswind, and torsion of the response of the downstream building. This was probably some of the first work that looked at all 3, including the torsion effects. Similar pattern, but yeah, it's a problem. If you want to do a PhD, and you're interested in this topic, speak to Capella. Take you on. So that's end of sort of wake excitation slash turbulence buffeting. The one that's left is your motion dependency. These tend to be pretty specific mechanisms for specific structures, generally lightweight or with a long after body. So bridge decks, where the flow comes along and you've essentially got a wing, or the solar panels that we've seen that rotate in torsional divergence. So these are just various mechanisms that have been researched. Galloping tends to be in one direction. Okay, the motion is what happens to the structure. Isolating wires, the translation response, and what's happening there is you've got an icicle hanging off the wire, swings around, and starts to go down like that, a bit like the Tacoma Narrows Bridge. So it goes up and down. Then you've got flutter, which has torsion in it as well. So flutter, it starts to rotate. The Tacoma Narrows was doing something like that. It's a combined flutter effect. Then you got lock-in, and because the object is moving, it generates its own vortex shed-in pattern. So when the object rotates, it's got a vortex that's coming off here, which creates a large suction pressure under here, and then you've got another one that's going to come off here, and it's going to kick it right back. And if that just moves itself, the wind speed could change, incident wind speed could change, but this is generating enough vortices just by its own motion to excite itself. That's lock-in. And then you've got torsional stuff, again, bringing more complex responses. And it's normally bridges and things with a long after body that are most sensitive to these things. As soon as you make it squashed and square, you might have stroll number effects, but they're not going to have a significant motion dependency. The circle won't have a motion dependency thing because it doesn't matter what way you move it, it's still a circle relative to the wind. Ovaling is a different one where it starts like that, and then as the wind blows, it sort of does that. It ovals in and out, which is quite funky to see. But it's only for thin, hollow structures such as gasometers that occurs for. A normal chimney or something like that is too stiff and rigid. It's not going to, it's too small. It would have to be a massive cylinder so that your resistance would be so small. So that's all your mechanisms. Once you've got your peak along wind load and your peak crosswind load, how do you combine them? Because they're never going to be simultaneously. So if you were looking at, you saw from the last slide that you got these little ellipses. For any wind direction and wind speed, the structure will probably be moving in an ellipse. And it can be simplified into an ellipse. Okay, so you've got your mean component in the middle, and then you've got your fluctuating component in the along wind direction and the crosswind direction. But what's your peak? Well, your peak there is, well, it's your peak crosswind in this direction, vertical axis, peak crosswind, but your mean along wind. Or over here, And this is where you really need to have good discussions with a structural engineer, because they know what's important for their structure. It may be bending in one direction, it's handle that quite well, but it can't handle bending in both directions. It's a lowly wind engineer. I can tell you the wind loads on it and the response, but is that response important enough for your structure? Hey, that's you. So it's important to tell them. The plot on the bottom right is similar for a building, tall building, but it's the base bending moment in the two body axes. So along wind, well, in the X direction and in the Y direction, let's call it. And from a wind tunnel test on a base balance, it gets tested at 36 different wind directions. Okay? So that's 36 ellipses there. And in each ellipse, you've got the grey squiggly stuff is what's happening. That's what the building is doing. And then these are the assumptions as to what your peak responses would be. It would be an envelope of this. So this would encompass all wind directions, all at critical, ultimate limit wind speeds. And then you would lie somewhere on the envelope of that ellipse. So from a wind engineer's perspective, that's what it does. You give that to a structural engineer and they'll go, well, what do I do with that? And so you've got to, again, talk to each other and you sort of say, well, let's pick your biggest MX value and we'll combine it with some value there. Okay, so that's the simultaneous value. That's your peak MY, your negative MX, and your negative MY. And then the other ones are the peak in a quadrant. So if you were looking from the middle out to the edge of the ellipse, that was what your biggest load would be in each of the 4 quadrants. The problem when you start doing this is you start getting results that come quite close together. So this is how you could automate it, but hey, the structural engineer might say, oh, no, I need that one. That's the one where I'm really weak because my foundation, I can't put a pile down in that corner of the site. So I'm restricted as to what I can do because there's a tunnel under there or something stupid like that. The wind engineers, tunnels, sorry, no idea. But I need to know that. We can easily get value, speak to us. And so that's where communication among engineering disciplines becomes exceptionally important. Not just wind and anything, it's anything and anything. Just keep the channels of correspondence open. So that's a combination of loading, which is really what the structural engineers finally want. They don't care about anything that we've done in between. They just want that load. And they preferably, they don't want 10 loads. They just want one load if they get away with it, because it reduces their workload. Yeah? But that's where it's at. So what has been done in the world to justify wind tunnel testing or to check that wind tunnel testing gives you the right answers? This was a PhD of mine a while back, and we instrumented this building, the Ernst & Young building down in the city. It's at World Square. And this was a building that got demolished and constructed all at the same time, consecutively. And we got to instrument the building and go in for a 3-year period to measure the natural frequency of the building and the response of the building once it was completed. We got to install instrumentation in there. So we had an anemometer on the crown of the building up in this corner. It was about the best place we could get it. We had GPS in it to try and get because accelerations don't give you the mean response, they only give you the dynamic response. So we needed something to try and help us out with the background slash mean response. And we tried GPS, but it failed miserably. It wasn't accurate. First thing was the estimation of the natural frequency of the building. So this is what Alan did to begin with, which was, well, there's the measured natural frequency. That's true. We've measured it. And he did, because he was working for the structural engineer at the time, he pulled out the model that they'd done on it. And that was the predicted natural frequencies. So if you look at these, they're all underestimated. Okay? What does that do to your response? If you underestimate your natural frequency, your mechanical admittance function is artificially over here rather than where it should be. And therefore you increase your response. Okay? Conservative. Oh well. Good, but you're wasting the planet and putting all those resources in there. Balance it. So he did added more elements into the FEA model. So rather than just having columns and beams, or columns and beams it would have been, he started to add the slabs, the lintels and everything else into the structure. And you can see that after that, you're getting a pretty good agreement with the, of a slight difference between the modes. So that's it. But the dampen level that we measured was quite low. When you're doing measurements of dampen, you've got to excite the building. How do you excite the building? Big building, because you don't want to have it by the wind, because you don't know what the force is. So you can either take a bunch of people like us up, as long as we've got rhythm, and we know the natural frequency of the building, because that's obvious. You can push on the building, like pushing a swing, and it will move. You will be able to measure the response, but you're not going to give it a big response, and therefore you've not activated all the mechanisms in the damping. So you've not activated all the cracking, you've not moved cables and lift shaft or anything like that. So that's why the dampen levels here, measured and expected, are probably slightly different. Still quite high, even at serviceability limit states. You'd be expecting between about 0.5% and 1%, and they're closer to the 1% level, which is good. Because your dampen is the other bit of the mechanical admittance function. If you can reduce that peak, then you will reduce your response. And then the accelerations is what we measured. So the building response that we got, you know, you have instrumentation in the building for 3 years. You're relying on Mother Nature to give you a good storm. We didn't get many, unfortunately, but some of the good ones were here. So you're getting up to a mean wind speed of about, mean wind speeds here, so you're getting up about 25 meters a second at the top of the building, yeah, which is pretty good wind speed. And then you've got your response here in the north-south direction and in the east-west direction. So we've got the southerly wind, so this is long wind, and this is crosswind. A bit of a block of a building, it's like a brick on its side, so it's not really got that much excitation, but that was some of the stuff that we did. And then this is a comparison between different wind directions. So from the south, which was the one that you saw, and then from the west, then that's the mean wind speed. That was the predicted, acceleration from model scale, and that was the measured. They're pretty good. So we were quite happy. He got his PhD. He lived happily ever after. That is the end of theory of vibration lectures. Has anybody got any questions? What the have you been talking about for 3 weeks? Nobody? All experts. That's what I like to hear. Has anybody looked at assignment 2? Would people like me to walk them through assignment 2? If you're not doing assignment 2, feel free to leave. Because that's what we'll do for the rest of the
Just going to put it on this.
Get an early mark. Right.
Go to bridge early.
Yeah, I'm gonna stay.
You guys will get questioned tomorrow.
Your quiz is at work tomorrow.
Again tomorrow.
Big enough? You guys can read that. Guys can start reading it and ask if you've got any questions.
Question.
Go for it.
I'm not sure if it's available for us on Canvas.
What?
Submission page, but the PDF is not available. It might just be locked.
Hopeless. Right.
I think that's why no one's read it so far.
Oh, that's your excuse, is it? Blame Michael. Bloody hell. Yeah, no problems. All right, I'll deal with that tomorrow then. But hopeless. I think we'll be able to do it from here. Way too complicated. Okay. So your local council has issued a compulsory purchase order on your block. They're going to build themselves a nice new building with a minimum floor area of 225 square meters and a height of 90 meters. Okay, that may be in a suburb that you think would never get planning permission. It's council, so they can do whatever they want. Okay, that's what they're doing. They're kicking you out of your house, and the block's not 225 square meters. They're building your neighbour's block as well. Okay. So, on the roof of the building will be a 15-metre high flagpole. Okay, so it's up to you to take your site block, work out what you're going to do on it, and a building that's going to have a floor plan of at least 225 square meters. It can be bigger if you want it to be, and a height of 90 meters. And it's got a flagpole on the top. Got a 50-metre high flagpole constructed from that circular hollow section. So okay, that's it. That's what the geometry looks like. You've got to work out all the dimensions of the building. Okay, plan form, height. It's got to be at least, it's got to be greater than that, It's got to be greater than that. So plan and elevation, you've got to put just sketches, doesn't have to be detailed drawings. Orientation of the tower to the north. This is be dependent on what your block orientation is. To keep the marker happy, so he's got to think about each design. And it also means that you can't copy off each other, which is really the main driver. Okay, orientation to north. So all you're going to do is have a plan forming your building and a north arrow. Okay. That tells us exactly what the wind directions are going to be. Also, you know, you're all living in Sydney, then you're going to be region A2. It was fun during COVID when people were working from all over the planet. So they were saying, what do we do about design wind speed? Just assume you're in Sydney, but your building's in China. So that was it. Okay, your design shooting, blah, 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 da, da, da. Okay. So, your first thing you're going to do is work out what your surroundings are, both in terms of shielding for the building. I mean, if you're down in the middle of the city, then you're probably going to have a little bit of shielding about you. Although in the 2021 version of the standard, you can't use shielding if your building's greater than 25 metres. And the reason for that is because of the interference effects that we saw tonight. Okay, there's too many unknowns in there. But topography and terrain category are the important ones. So you're going to look at that in a north and a cardinal direction viewpoint. So ignore the building, you're looking at that in those 8 quadrants as to what is happening. If you're in the middle of suburbia way out west, then it's nice and easy. If you're at the coast, Vaucluse or something like that, you've got ocean on one side, you've got suburbia on the other side, and you've possibly got topography in the middle. Yeah? So you've just got to build up and justify all your MZ-CATs, your MTs, your MSs, MCs, and everything else for that design. The reason that you're a 90-metre tall building is that it means that you will have dynamic effects. You will have to consider dynamic effects. So you will have to use section 6 of the standard. Every other assignment you'll have in your undergrad, you only go up to section 5 of the standard if lucky. Okay. So 500-year return period design overturning moments in both the along and crosswind directions for the building and the along wind load on the flagpole, with and without a flag. You can put your flag on, you can put what size of flag you want, what shape of flag you want even, and do that. Would you imagine that the flag and flagpole would have a big impact on your building response? No. So if you do your calculations, you do get a big response, you're probably wrong. One of them will be wrong. But we'll get back to that flag later, especially when we start looking at the mast itself, because the mast is similar to what we were looking at tonight in terms of its dynamic response. Okay, so in the standard, we're looking at the base overturning moment, winds coming this way, both in the along wind and in the crosswind directions. It's up to you where you've got your core in the building, etc., and the torsion that would be in there. Now, or maybe just the standard. So in the along wind direction, go back. So once you've done this, you're going to have your MZ cats and your MTs and everything for all directions. You will then say have, let's say, design wind speeds, directional multipliers and all things like that in there. So that'll be your distribution of design wind speed, say at the top of the building. Okay. Then you overlay your building onto it. So let's say it's oriented this. And you will look at 90 degrees to each of the faces of the building. And you will pick the highest wind speed in that quadrant to be acting on that face of the building. This one is probably that one, the way I've drawn it. Probably that one as well for that one. There, so it's that one in that direction. Okay. That's your first thing, is to set up your design wind speeds for the building faces. So what you do in the code is you take the biggest wind speed in that quadrant and you assume that that is applying orthogonal to the face of the building. Now the reason for that is because your peak response is not necessarily with the wind bang onto the face of the building, but it could be from wind tunnel testing, it could be anywhere in that quadrant. So that's why it's simplified down. So again, it's an added conservatism in the standard. Okay. Once you've got that, now if you've got a rectangular building, you only have to consider the two worst cases. There's no point in doing that one and that one if that one's worse. Yeah? Just do the worst case. So if you've got a rectangular building, you'll be looking at two wind directions. If you've got a square building, you'll only have to look at one wind direction. As long as your site permits. Okay. So you've had hint number one to make your life easy. Right, now we can go into calculating the along wind and the crosswind loads. So for your along wind load, typically you would split your building up into sections, about 6 or 7 sections with height, and you will calculate the wind speed at the middle of each section. Okay, so you know what your MZ cat is with varying with height, so you can define what your wind speeds are up there, and you can calculate what your, again, we're trying to calculate the peak moment based on the gust wind speed being applied everywhere at once. That's section 5 of the standard. Okay. And then section 6 is bringing in the reduction or increase in your loading due to the dynamic effects. Okay, so this is essentially section 5. You're looking at your windward face. So your C fig over here is probably going to be about 0.8. And your C fig on the leeward side is probably going to be about minus 0.3 to minus 0.5. Okay? So you know what the wind speed is with height, you know what your windward and your leeward pressure coefficients are, and therefore you can calculate the force. Noting that this leeward one is based on the wind speed at roof height, whereas your windward ones are based on the wind speed at the mid-height of each of the sectors.
How many sections do you think we should do for a 90-story building, or 90-meter building?
90-meter building. A lot of consultants would do level every story. Excessive. I would be tempted on a 90-meter building to use something like about 15, 5-story, yeah, or even 30 is probably pushing it, yeah. So I would be thinking about a 15-meter sector. Try and split it into logical heights, or you can try and split in heights as per the standards, so that you've got to get your MZ cats at the level of the building. Yeah, lots of ways you can try and make your life easy. There's no right answer here. There's wrong answers, but there's no right answer. There's just more right. Yeah. Don't go into too much detail. As we've hopefully seen by now, this is not a precise science. So going down to one level, you're probably putting too much emphasis on the accuracy that really is not there. Yeah? Keep it pragmatic. So once you've done this, then you can calculate your base over ton and moment. Then you've got to put in your C-fig value, which is just a case of going through what we've been talking about today and last week. Factor. Your crosswind response is only from section 6 of the standard, and that will give you your crosswind response based on what we've talked about today. And on this point, I will open the standard up to talk you through that a little bit. Well, this you should hopefully be able to pull this from Tech Street. Go through all this stuff, section 5. For your long wind, you're only interested in that and that. You don't care about your internal pressure because it's acting there and there at the same time. It's got the same pressure, so they cancel each other out for the overall response of the building. But they will be important when you start looking at cladding pressures. So skip through all. Well, I can probably go back up and just show you where to go for. Leeward wall. So there's your leeward wall section. So depending on what you do upon B ratio, you're going to have a flat roof, so you're going to be in there. So your external pressure coefficient is going to be one of these three, or linear interpolate, depending on your D upon B ratio. Your building's over 25, therefore your CPE on your windward wall is 0.8, varying with height. Whereas your leeward wall is based on the wind speed at mean roof height. Mean roof height, not mean flagpole height, because that flagpole is going to do nothing to the wind speed over the top of the building. Okay? And you're going to go to section 6 for your long wind response. So section 6.4 is going to be this one. This is the equation that we've seen for the last 2 weeks. Just work your way through that and find out what C dyne is, noting that C dyne will probably be less than 1. Don't be concerned if it's less than And then your crosswind response is down, further down. 5 here. You can do this in two different ways. You can calculate your static crosswind force up the height of the building using this equation here. One way to do it. Or you can shortcut it and go straight to your crosswind base over turning moment. Use this equation here. My recommendation would be to use this equation. Now, your crosswind force spectrum coefficient, which is what we talked about tonight, you can either calculate it by these equations, or you can pull it from these graphs if you use this. So we showed you some of these graphs earlier tonight. So you've got reduced velocity on this axis, and you've got your log 10 of CFS on this axis for two different turbulence intensity values. So depending on the height of your structure from this table here, and on what terrain category you're in, if you're a 90-meter tall building, you're going to be about 0.16 at the top of the building. It's at 2/3 of the height, so down at 60 meters, you're going to be about 0.18, 0.19, roughly. So therefore, if you've got a 3-to-1-to-1 building, then you're going to be pulling it off this one. Again, going back to the lecture earlier tonight, why do we find that at smoother flow, we get a higher response here compared with turbulent flow? Whereas down here, it flips around. We get a higher response when we've got turbulent flow here. Who would like to answer that exam question? Everybody's avoiding eye contact. Go for it, look.
Is it just not the same that it's turbulence buffeting instead of vortex shedding?
Yep. And so why is it going this way?
Wait, so the dotted one is
Turbulent.
more turbulent. Well, there you go. You know, it's more turbulent at lower velocities.
Mm-hmm. And what about here?
Um,
Why does it flip over?
Maybe if it's normalized, then it's like a higher portion of the.
That is normalized.
It is. So then,
CFS is a normalized value.
okay, so essentially for less turbulent flow, a higher portion of the dynamic response is from shear layer interaction.
So we've got a reduced velocity of 10.
Yeah.
We know that the excitation mechanism is wake excitation. Yeah? So why does the lower turbulence give us a bigger result?
Can you give us a multiple choice?
Can I give you a multiple choice? I could do. Or I could just give you the answer, which might be even easier. It's because the turbulence in the flow breaks up the correlation of the vortices. So when you've got, imagine you've got a building and you've got, the wind is doing this on it, yeah? The vortex up the height of the structure is going to be broken up, yeah? It's going to be messed up. And that's why you get a lower crosswind force, because you've got really smooth flow, and we go even further and we say, right, we've got absolutely laminar flow, yeah? We will have a beautifully well correlated vortex